again, it's all deserted now. You can see the drag on the faults. See the fault through there. See the sediments are all dragging up like that, so it's a normal fault in here. And then if we look down in here, we see these secondary minerals but vertical vein arrays. So a normal fault, vertical veins, extension. It's got the same structure as all the rest of the area. So it's probably related in some way, although it's a long way away from the Pluton, as I'll show in a minute. So we've got sheeted veins in the granites, we've got skarns, we've got things outside which are a lot more. So a lot of this is very clearly related to the Pluton, and then we get a whole lot of other things out here which we don't know. Because we've got orogenic gold in the area, we're not sure. This Pogo mine, for example, the average grade is 17 grams per tonne, and it's full of subhorizontal veins. So although people put it in here on a structural basis and a grade basis, it's an orogenic gold system. They thought it was the same age as these, so this was thought to be the big one, the nice one with high grade. But when they dated, all of these are 92 million years old, and this one's 105 million years old. And the stuff at the other orogenic gold deposits in the area also, ones we think are 105 million years. So it probably isn't. So you probably don't heard of these things anyway. So that's what the model looks like. The Pluton, sheeted veins, skarns, other things around it, and then maybe these silver veins way away outside of the influence of the granite, all with this sort of vertical extensional structures. Just to give you an idea, see all the ones that are in the granite are all about 1 gram. They're just similar to, they're at the high end of porphyry copper gold systems. 1 gram seems to be something. Some of the deposits are maybe 2 grams. Up in here we can see Pogo. Look at Pogo sitting up here, high tonnage, high grade. It's nothing like the deposits that are down in this area where we can relate them. And as I say, these are all 92 million years old, and this is 105 million years old. So it's almost certain. Won't worry about all these things. We'll get on to the granites. Everyone happy? You've just got a bit of an overview. I don't want to go into detail here, just give you a bit of a picture of what is what's going on with these type of deposits, just to see if you've seen anything like it really. Have you seen anything like this anywhere here? Or anyone recording anything like it? And then we look at the granites, and again I'll skip through this quickly because today is really toughest day. Yeah. No. That's what I'm saying. So what's happening basically, if we look at these, it's the end of deformation. So we had a look here. So basically, if we just had a look at where these things are, so we could draw a little cartoon, basically, I suppose. So what we've had, say, we just put a number 1 here. We've had number 1. We've got a belt of sedimentary rocks which are overlying. So we've got a craton sitting here somewhere, maybe with a few bits of it. So this is craton, old Precambrian. Craton. In there, we've got a whole lot of sedimentary rocks formed over it like that. And then number 2, we've had the craton doesn't change in here. And then we've had a whole lot of thrusts that are thrusting these materials over each other. Like so. Here's the craton. Here's the craton. So that's deformation phase. Like that. And then 3, we've had that effectively. So we've got our craton like that, and craton like this, and we've had all these thrusts. So we've got all this structure like so. And then what we've effectively had is just a slight extension, like so, due to this thing coming through and a bit of a stenosphere coming in, and this is when we get our granites. Just that little bit of extension and a stenosphere coming in causes the mantle melting, or the flat subduction zone does it. Right? But this is essentially, as Phil said, it's sort of static. There's nothing, there's no deformation going on at all. Everything is post all the compression, so all the folds, all the faults are all there, and then this just comes in and all the deposits are undeformed.
So
Yeah.
What do you see? So you see these systems in North America. Why don't you see them in the Precambrian grass, the Abitibi and Yilgarn?
Yeah. Well, the reason you don't see them in the Abitibi and the Yilgarn is that you need, as I'll show from the magnetism, you need a craton. So you need to be on an Archean craton boundary, right? And you probably need to be on an Archean craton boundary that's had 2.7 billion year subduction and so on, because that's when most of the alteration occurred, because that's when most of the crust occurred. So most of the metasomatism of the lithosphere probably occurred at 2.7 and 2 billion, when all these orogenic gold deposits were forming as well. So you don't expect to find these in Archean cratons, because you need the Archean craton to form the magnetism. And then they're going to be, you could form them in Paleoproterozoic because you've got an Archean craton. And if you look at Mali and Guinea and so on, they're on the edge of the Man craton in West Africa, and there are lots of evidence as founded subcontinents. There's lots of, the isotopic evidence to me suggests there's lots of bits of craton margin out there under Mali. So I think that's why you see these things. And then as you get younger and younger, you should see more, because you've got lots of craton margin, and there've also been lots of subduction under them, and you've got lots more metasomatism. So the lithospheric margin is juicier now than it's ever been, if you like, through history. That's what I think. I've actually got some slides. I'll give you a set of slides that show you why you won't get them in the Yilgarn. I actually made a talk, but that's the answer. That's the answer. So you need the craton. I'll show why in a minute. You need metasomatized. See, what happens is, under these cratons, underneath the craton, all the time you're getting subduction. And when you get subduction, all the fluid, all the sedimentary rock, you know, if you imagine the ocean today, right, it's full of sedimentary rocks. They've got iron in them, they've got carbon in them, right? On the seafloor, you've got all these manganese nodules that are full of nickel, copper, so on. You put those down the subduction zone, and they dehydrate. All this stuff comes up into the bottom of the craton margin. So that's why I was interested where the old rocks were in Egypt, for example. So these are juicy places. Lots and lots of action is going on, and all these get metasomatized. And one of the incompatible elements that's going to go into the fluid is gold. So I think these zones are enriched in gold. So I'll show that now here. We've got a geological setting. We've got something about the mineralisation we've done. Now we'll look briefly at the intrusive rocks, and I'll run through this fairly quickly, but we can see this is one of the most amazing sets of data I've ever seen.